Welcome to our project. Our project is Underwater Buried Object Detection and our guide is Dr. Srikumar Ji. So now we have reached up to 75% of completion. It is a pure software based project in which we are doing program codes and object detection using MATLAB. In order to detect the object under the seabed, we use the data provided by NIOT. NIOT means National Institute of Ocean Technology. The data is in the form of a matrix, which is a received signal from seabed after several reflections. So, coming to abstract, now I'll give the basic idea about the system from which we get the received signal. It is an indigenously developed buried object detection sonar, also called BOTS, used to find targets in the seabed. The important features of BOTS are it has wide bandwidth from 2 to 24 kilohertz. It has a lightweight projector weighing up to 21 kg and a computer-based real-time signal processing. The reflections from the experiments done by NIOT at shallow waters are used to detect the seabed boundary layer and targets like metal plate and concrete blocks, etc. Sediment layers and the targets are distinguishable in the BOTS image. Coming to introduction, BOTS is an active sonar system for detection and real-time imaging. Now let's see the basic blocks included in a BOTS system. It consists of two subsystems, tow body and deck side, in which tow body consists of an acoustic transmitter, receiver hydrophone array and a GPS receiver. Deck system consists of a signal generator, power amplifier, data acquisition system, signal processing unit and power supplies. Tow body. As I already said, an acoustic transmitter, receiver hydrophone arrays and a GPS receiver are mounted in a floating tow body. The tow body has a dimension of 1.75 meter into 0.70 meter into 0.30 meter and it is stored at a speed of 1 to 3 meter per second behind a vessel. The photograph of the tow body during sea trials is shown in the figure. Coming to the fabrication of tow body of BODS. Bottom view of tow body is shown in this picture. It can be fitted with maximum of 4 hydrophone arrays or 32 elements in the present design. The figure consists of 16 hydrophone elements. They are arranged as 2 linear hydrophone arrays in the tow body. The backscattered signals are acquired by the 16-channel symbol hydrophone array. Each row consists of 8 sensors along the length of the tow body with 0.0325 meter as the spacing between the elements. Then coming to deck system, I have already mentioned the components of deck system in the previous slides. The purpose of deck system is to store the raw data and process it, followed by the real-time image generation. Now coming to the basic block diagram of our project. This shows the main steps of our program code. Raw data from 16 channel hydrophone arrays given to filtering, then beam forming, match filtering with the reference signal, Hilbert transform, imaging. Based on these steps, we have divided our work to find the program codes for each step, combined it to get a whole program. Now, what is beamforming? It is a method of observing signals from a desired direction while attenuating the response of the array to signals from other directions. That means it is a signal processing technique used in sensor arrays for directional signal transmission or reception. This is achieved by combining elements in an antenna array in such a way that signals at particular angles experience constructive interference while others experience destructive interference. Beamforming can be used at both the transmitting and receiving ends in order to achieve spatial selectivity. The hydrophone array output is connected to simultaneous sampling of 16-channel data acquisition system. Raw data from each channel corresponds to 3456 samples. This is stored in a matrix format, and these reflections are provided by NAOT. The 16-column data is focused using a conventional beamforming technique. So next step is match filtering. That is, after beamforming, the next step is match filtering. It is a frequency domain match filtering we are using here, which improves the SNR of beamformed output. In signal processing, a match filter is obtained by correlating a non-delayed signal or template with an unknown signal to detect the presence of the template in the unknown signal. This is equivalent to convolving the unknown signal with a conjugated time reverse version of the template. The match filter is the optimal linear filter for maximizing the signal to noise ratio in the presence of additive stochastic noise. Then output we get from the match filter is the product of complex conjugate of transmitted signal and the FFT transformed received signal. The output from match filter transferred back to time domain in order to do the image mapping.
So now we'll look into the timeline of our project. During the month of August, we were looking through different IEEE and research papers. We selected an area of study and with the help of our guide, we fixed the topic. September was the time where we proposed the project plan. This basically included the current problem of the system, our aim, benefits of the project, deadlines, costs, and also the success criteria. It was taken into consideration that equal participation should be given by each group member. By the beginning of October, we were studying different sonar principles, and we also got in touch with the people who had already done a project in this area. This helped us to understand the difficulties that they faced during this course of time. At the mid of October, we started looking for seminar papers, which also helped us to understand the different angles of our project. November was the time where we divided our task and each group member was assigned to study different methods of object detection. And finally, we selected a particular technique, that is edge detection. For this, a code was developed and edge of a particular known image was obtained. Each group member also did a seminar presentation on the area of the project based on the IEEE base papers that was already selected by us. In December, we developed a code with the help of generated chirp signal. This code was tested and alterations were made until the desired output was obtained. In January, we received the NIOT data. This data was tested in the above code. Troubleshooting of the error was done by different group members until the final required output was obtained. February was a time when we started looking for alternative methods instead of FFT in match filter algorithm. We came to know that FrFT, that is fractional Fourier transform, was the most suitable method. In March, we compared both the output of FFT and the FrFT code. Different features of the same were studied and we started imaging both the codes. For this, different group member was studying different imaging techniques. This corresponds to the 75% of our project. For the final 25%, what we plan to do is that imaging of both the codes with respect to depth. Thus, we can do a performance comparison of both the algorithm. And as a final step, we have to document all our observation and prepare a final report on the same. Now we'll see 30% of our project. At that time, we were not provided with the NIOT data. So we decided to look into different object detection techniques. Because our project was basically under the image processing section. Each group member worked on different techniques and a detailed study of different methods was done. And finally, we chose a certain technique for edge detection. As the 30%, FFT of a known image was found. For this, in order to get proper FFT, the values should be centralized. And after centralization, we obtain the values as a huge number. So in order to plot those values, we had to find the log transform of the same. And as a part of next step, we had to filter those values. For that, we use high pass filters. And finally, we only require the numerical values. So we converted a value into spatial domain. Now we'll see the 30% block diagram of our project. So it's basically edge detection using FFT. For this, we'll consider an input image, that is a known image for this process. So this known image is of RGB format. So it has to be converted into a grayscale. And the next step is Fourier transform. And after that, we perform log transform because Fourier transform values are quite large. So in order to plot these, we perform log transform. And after this, in order to plot or in order to obtain an image, we perform high pass filtering. And after this, we'll get a final output image, that is the edge detected image of the input image. As I've explained earlier, we have chosen a known image as our input image. So on the screen you can see the image that we chose as an input image. So it's basically in the RGB format. So this is the image that we process for our 30%. So now we can see the results of our 30%. As I've explained before, we've taken a known object or a known image as an input image. So it was basically in RGB format. And as a result, first image we obtained is a grayscale image, that was the converted form of RGB to grayscale. And on the right side, we get the log transform in the frequency domain. And also similarly, a filtered log transform that is also in the frequency domain. So what we can see as a similarity is that both these images in the frequency transform, we cannot actually identify the original image. But in case of the spatial domain, when we obtain the high pass filtered output, we can clearly see the edges. Actually, the edges are obtained or edges are detected in the final high pass filtered image. And thus the final output of the image is obtained. Now we'll look into the different steps involved in the 50% of our project. At this time, we were not provided with the NIOT data. So with the help of some background research, we came to know that the NIOT data is basically a chirp signal. So what we did was we generated a simple chirp signal. But with some further studies, we understood that this chirp signal cannot be used as such. So we added some noise to it. Next, what we did was we performed beamforming using time delay algorithm for 2D array. So what beamforming does is that it directs the signal in a particular direction. After that, we performed match filtering where the beamformed output is compared with the original data without noise, and the output of this stage will indicate the matched region. After match filtering, we did Hilbert transform. So Hilbert transform is basically a phase shifting transform where each component where the phase of each component is shifted by plus or minus 90 degree. And as the last step of the 50%, we performed fast Fourier transform on the NIOT data. Now, next I'll be explaining each step in detail. First is the chirp signal generation. So what is a chirp signal? It stands for continuous high intensity radar pulse. In simple words, it's basically a signal whose frequency increases and decreases with time. Mathematically, a linear chirp signal sweeps the frequency from low to high linearly. One approach to generate a chirp signal is to concatenate a series of segments of sine wave, each with increasing or decreasing frequency in order. This chirp signal is most commonly used in sonars, radars, and also lasers. Now we can see the code for the generation of a chirp signal. In the fourth line of the code, we see a phase dot custom microphone element. This creates a custom microphone element with a frequency vector from 20 to 20 kHz and a frequency resolution of 1. In the line phase.ula, it creates a uniform linear array system of objects. A default array is a 2-element ULA, but for our purpose we are considering 8 isotropic antenna elements with an element spacing of 0.0325. Since it is in the array format, we require a phase.wideband connector with all the above parameters. We took the incident angle as minus 50 degree and the azimuthal angle as 30 degree. Now we can plot the received data, that is the collected data, with respect to the incident angle, that is minus 50 to 30 degree. We plot this data with respect to time domain, and this is the input that we obtained. Next step is beamforming, where the input chirp signal is processed. The input chirp signal is broadcasted in every direction at once, and all these crossing signal causes serious interferences. Beamforming is like traffic signaling system for signals. It is used to direct and steer the composite microphone directivity beam in a particular direction based on the signal source direction. Instead of broadcasting in every direction, it would allow us to send a focused stream of data in a specific direction. Thus, it prevents interferences and it's way more efficient, which also improves the SNR. Now, talking about the advantages, it provides high quality and intelligible signal from the desired source. In the context of wireless communication, beamforming provides the means of maximizing an estimate for the transmitting signal's direction of arrival. Estimation of coherent signal sources has become increasingly popular technology in the fields of audio, sonar, and biomedicine. The uniform linear array, or the ULA, of 8 antenna elements along a single dimension that are spaced equally apart by some distance is shown here. The direction of arrival, or the DOA, can be determined and the spatial spectrum of the surrounding environment can be further classified. Since there are 8 sensing elements, the data is received by each sensor by a particular time. So this time is different for all the cases. But since what we consider is the ideal case, we are creating a delay using the keyword delayed phase. So this will produce a delayed output, and after getting the data from each sensor, they are given into a summer circuit. Here all the sensing outputs are added together and we get a single beamformed output, which is then given into a match filtered algorithm. A graphical representation is shown in this figure.
After talking about beamforming in the last section, the next step is in the process is match filtering. Match filtering is normally used in sonar application. So in match filtering, a known signal is sent out and the reflected signal is examined with the known signal. So it is basically an optimal linear filter that is used to increase the SNR. So here first the transmitted signal is sent out and the reflected signal is received, and this reflected signal is then measured with respect to the input signal, that is the transmitted signal sent out. So basically match filtering is obtained by correlating the input signal and the received signal, or known as correlating the known signal with the unknown signal to find out the unknown signal. In the slide, the block diagram given is the general representation of match filter. Here the input to the filter x of t is basically corresponds to two other signal. It consists of a pulse signal g of t and which is corrupted by a white noise w of t. The white noise w of t basically is a sample function of white noise which has a mean 0 and a power spectral density of n by 2. So this both corresponds to the input signal x of t, which is then given to the linear filter. So as the filter used here is linear, the output y of t is given by the expression given below. Here in the expression, g naught of t corresponds to the signal component of input x of t and n of t corresponds to the noise of x of t. So for a match filter to work properly, it needs to find an optimum manner to find the signal g of t in the receive signal. Here in this case the receive signal is x of t. This slide gives us the mathematical expression for match filter. From the above two slides, we know that match filter is a correlation function which is used to correlate the unknown signal with the known signal in order to find out the unknown signal itself. In match filtering, a signal is transmitted or sent out, and the received signal is then measured with the help of the transmitted signal. So from that information we can conclude that match filter is an equivalent to convolution of unknown signal with a conjugated time reversal of the input signal or the known signal. Based on that info, here is the expression for match filter. In this expression we can see y of k is the output of the system at time k. Considering the system has j numbers of sensors with k minus 1 number of time delay. Here the x of L is the unknown signal and W star is the conjugated time reversal of the input. Based on this expression, we have computed a code to find the match filter output. The match filter code will be discussed later in the PPT. So after discussing the various steps, here is the output of the text conducted using the generated chirp signal. So as you can see, the first plot shows the input signal or the generated chirp signal. In order to stimulate a received signal, we added white Gaussian noise to the chirp signal, and that signal is shown in the plot number 2. To focus on one particular direction, we used beamforming, and beamformed output is shown in the plot number 3. The beamformed output is then correlated with the conjugated time reversal of input chirp signal to give the match filter output, which is shown in the last plot. This is the result from the test we conducted. In match filtering, we use fast Fourier transform algorithm. So in this section, we'll be discussing fast Fourier transform. Fast Fourier transform is an algorithm that is used to compute discrete Fourier transform or its inverse. So it is used to convert time domain into frequency domain, or it is used to represent time domain in frequency domain, or vice versa. So this conversion normally takes very time, that is, it is very slow, but using fast Fourier transform algorithm we can do it faster. This can be done because in fast Fourier transform we'll factorize the DFT matrix. Fast Fourier transform also reduces the complexity when it is compared with DFT, and it takes lesser computational time by using the properties such as symmetry and periodicity. Here in this slide, we will be discussing the uses of fast Fourier transform. As we have previously discussed, we know that conventional fast Fourier transform is more faster than the discrete Fourier transform. So this is because it is fast Fourier transform factorizes the DFT matrix, which makes it more faster than DFT. So another advantage of this fast Fourier transform is that in case of any round of errors, this fast Fourier transform is more accurate, or it is more efficient when compared with DFT. Due to all these reasons, fast Fourier transform has many applications. So as you know, fast Fourier transform is fast, that is, it has high computational speed, it is more accurate, that is more efficient, it uses properties such as periodicity and symmetry. It has high number of application in signal processing unit. So in signal processing unit, it is normally used to analyze and detect of signals. Along with that, it is used to solve unwieldy equation to describe dynamic responses of electricity, heat or light. So when we are converting audio and speech signal, we normally use into frequency domain, we normally use fast Fourier transform variant in order to do so. Modulation techniques such as orthogonal frequency division multiplexing is one of the techniques that use fast Fourier transform. Fast Fourier transform is also used for noise reduction in mobile, audio and speech system.
Here we'll discuss about the way to compute FFT. So there are many ways for computing of FFT. So among all these ways, we are going to consider butterfly method. So butterfly method is an easier method for computing of FFT. As we know, FFT is basically factorizing of DFT matrix into a sparse matrix, which is basically mostly zeros. So in this butterfly method, the DFT is decomposed into log n to the base 2 stages. So in each stage, there consists a n by 2 butterfly computation. So in this diagram here shows butterfly computation. So here in each butterfly we will have two inputs, that is two complex numbers, and using this two complex number we will produce another set of complex number, that is we will produce two other numbers. Like shown in the diagram, we have two complex numbers p and q. This p and q is used to produce a set of complex number which is p plus alpha q and p minus alpha q. Here alpha is another complex number. So this is one of the way in which we can compute FFT. Now we will discuss about the MATLAB code. This code is used to find the presence of object in the received sonar data. So this system here, it is implemented using FFT to compute match filtering. So in the code we can see the load function. The load function here is used to load the data provided from the NIOT to the code. The data from the NIOT consists of both the input signal as well as the received signal from the hydrophone array. So in order to implement the code, first we need to stimulate the environment. That is, we need to stimulate the hydrophone array system. This is done using the command face.ula. So face.ula is used to stimulate a uniform linear array. Here we will be considering 8 elements with a spacing of 0.0325 centimeter between each sensors. This data received data will be from 8 sensors. The received data, the NIOT received data is a 3D matrix. The size of the 3D matrix is 1536 into 8 into 11 elements. Then the input or data from NIOT is plotted in the code. Since we have already plotted the input signal, now we will be plotting the received signal. So the received data is from 8 hydrophone array. It is a 3D matrix. The NIOT received data is a 3D matrix of size 1536 samples into 8 into 11 elements. So in order to plot the received data, we will be considering each element from the 11 elements and plotting them separately. After this, we need to perform beamforming on the received data. In order to perform beamforming on the received data, we will be using the command face.timeDelay beamformer. Face.timeDelay beamformer is used to perform time delay beamforming on the received data. The need for time delay beamformer is already discussed by Alicia under the beamformer section. So after computing the beamforming of received signal, it is plotted using the plot function. After beamforming, the next step is to perform match filtering. So to perform match filter, first we need to compute the fast Fourier transform, that is the FFT of the received signal, and then we need to conjugate the input signal. So after calculating both of these, then we will be convoluting the fast Fourier transform of the received signal and the conjugate of the input signal to get the output of the match filter. Then the output of the match filter is plotted using the plot function. This slide shows the output of applying the code to the NIOT data. So the first graph here shows the input signal, that is the signal transmitted by the NIOT to find out the interferences or the depth or the buried object. Now the second graph here shows the received data, that is the received data from the 8 hydrophone arrays considered. So the data received was in the form of a 3D matrix of size 1536 into 8 into 11 elements. So from these we then performed beamforming and we got the output shown in the third graph. After this, the fourth graph is the output of performing match filtering on the beamformed output with respect to the input signal. The next section will be explained by Anjali.
Fractional Fourier transform, or FRFT, is a family of linear transformations that is generalizing the Fourier transform. It can be thought of as a Fourier transform to the nth power, in which n need not be an integer. It can transform a function to any intermediate domain between time and frequency. Some of the applications of fractional Fourier transform are filter design, signal analysis to phase retrieval, and pattern recognition. FRFT can be used to define fractional convolution, correlation, and other operations. Some of the properties of fractional Fourier transform are additivity, commutativity, associativity, linearity, inverse, time reversal, etc. Underwater scenario with all its complexities has been always very challenging for the sonar signal processing. Because of reverberation and fast-fading nature of the channel, it is necessary to use chirp waveforms for sonar transmissions. The conventional techniques, which is based on Fourier transforms, often fail to fully address the issues such as Doppler estimation with chirp waveforms and low signal-to-noise ratio detection due to the medium. So, we have fractional Fourier transform, which is also known as FRFT. It can be used in sonar signal processing for improved chirp detection performance. However, this useful signal processing tool is largely unknown to the sonar signal processing community. So in the coming slides, we will be learning more about fractional Fourier transform, and also we'll find out why we chose fractional Fourier transform over fast Fourier transform. Uses of fractional Fourier transform. It is used in time frequency analysis and digital signal processing. It is used to filter noise. That is, we can filter noise with the help of fractional Fourier transform. The condition is that it should not overlap with the desired signal in the time frequency domain. In the case of intercept sonar, fractional Fourier transform can be used to estimate parameters of chirps from multi-component signal. Also, it can be used to detect and identify the emitter. In the case of active sonar, FRFT has great potential in sonar signal processing because it takes advantage of the knowledge of transmitted waveform. Fractional Fourier transform can be used in sonar signal processing for improved chirp detection performance. So these are some of the uses of fractional Fourier transform. Comparison of fractional Fourier transform and fast Fourier transform. In this slide, we can see two figures. Figure 6, that is fast Fourier transform of chirp without noise, and figure 7, fractional Fourier transform of chirp without noise. As you can see, the spectrum of the chirp signal will be spread in the case of fast Fourier transform, whereas in fractional Fourier transform, it appears as an impulse. This is because the fractional Fourier transform output for the optimum transform order is highly concentrated. Hence, it appears as an impulse. We chose fractional Fourier transform instead of fast Fourier transform because we can save computation time as well as calculation. Instead of calculating the spread spectrum, it is easy for us to calculate the impulse, which is obtained in fractional Fourier transform. Hence, we can also conclude that the energy of the chirp signal is concentrated well in the FRFT domain rather than in the FFT domain. Also, there are many other comparison criteria of the FRFT and FFT, such as efficiency, performance, etc. So, all these things will be evaluated in the later stage. Computation of fractional Fourier transform. To compute fractional Fourier transform, we require the value of alpha. The parameter alpha is known as fractional order or fractional power. To compute this, we require a formula, that is B is equal to F1 minus F2 by 2t. Here, F1 and F2 are the frequencies, whereas t is the time period. F1, F2 and t can be found out from the graph which is shown in the slide. The next formula is to find phi, where phi is equal to tan inverse of Fs square by 2bm. Here, Fs is the sampling frequency, B is computed from the above equation, and M is the number of samples which is taken or considered. So, alpha, that is the fractional power, is equal to 2 into 5 divided by pi, where phi is computed from the above equation and pi is the pi value, that is 3.14 or 22 by 7. Testing of fractional Fourier transform. Fractional Fourier transform for the input and received signal was checked before applying directly to the match filter. So this is the result which we got after applying the fractional Fourier transform to both the input signal as well as the received signal. When we checked the FrFT code, it was not directly available. So to do the FrFT, we added an additional function, FrFT. So we downloaded the code of FrFT from online and then we added it to the MATLAB workspace. So in order to apply the FrFT code, we required a parameter alpha, which was calculated with the help of a formula which was discussed earlier, that is on the slide of computation of FrFT. So with the NIOT data and the alpha value, we found out the corresponding power and then we applied it to the code, to our MATLAB code using FrFT. So we got a result which was close to the result which we got for the fast Fourier transform. And we were able to find out that the computation time for FrFT was very less compared to that of FFT. As you can see, the MATLAB code with NIOT data using fractional Fourier transform is very much similar to that of the code which we have used for the fast Fourier transform. The only difference is in the match filter section. That is, instead of FFT, we have taken the function FRFT. And also, we have taken the conjugate of FRFT instead of the conjugate of FFT. So this is the only difference between the FFT data and the FRFT data. And we have got the result in which both the FFT values and the FRFT values which we have obtained is exactly almost same. Result. This is the result which we got. So first one is that of the input sonar signal. Second is received 2D signal. So you can see there are two parts. First part is of the air-water interference, which we can ignore. And the second part of the signal gives us the information about the buried objects. Third one is the beamformed output. And for the fourth, we have got the match filter output in which we have applied the fractional Fourier transform. Future work. So regarding the future work, our next step would be the performance comparison between fast Fourier transform and fractional Fourier transform. That is, we will be dealing with different performance criterions and we will be evaluating it for both FFT and FRFT, and then we will conclude which one is better. And the next step will be imaging of the sonar data using both FFT and FRFT by using the surf plot. We will be getting images and we will check which one is more precise and accurate. We have also submitted our report for the first 3 chapters to our guide, and hopefully within a few weeks we will be completing our project. Thank you.